Okay, so today we are going to talk about Hall effect, the simple classical one, not quantum one. So, we know about Hall effect, but the aim of this presentation is to get the formula for Hall effect on the backhand calculation, just piece of a napkin or something like that. So here is my sample, width is W, thickness is T, and I have applied current in this direction. Magnetic field is perpendicular, that is out of the plane of this paper. What happened is because of the magnetic field, you have a magnetic force to the sample q v cross b, and which will tends to move the charge carrier towards one end depending upon the size of the charge sign of the charge carrier, like positive or negative. So in case of electron, this will go there. Okay, so this is my sample and this is how the voltage is developed, so you can measure voltage here. So the typical sample in lab, it looks like this. So you make, this is called Hall bar geometry. So you pass current through here and you will measure longitudinal resistance here, and you measure Hall resistance here across these two terminals. Okay, in practice, if you're passing current through here, you should not get anything here, but as soon as you switch on the magnetic field, you get the Hall voltage. Now I'm just giving you a formula for the longitudinal resistance. You have to take in granted this is rho xx is equal to m over ne squared tau. But we're not going to derive it. Just for the sake of completion, I will give that. What we're going to do, we're going to derive Hall resistance. So if you see, Hall resistance is RH is equal to VH upon IX. So VH upon IX, and so we have to find out these terms one by one. Now first we are going to find Ix, okay, and then we'll see what is VA. So for Ix, we know current density is current per unit area, and then area of cross section is W into T, and then you can get Ix from here. And one thing I have to take it from the books is Jx is equal to NQVx, and then you plug in this number here, so you get Ix is equal to NQVx into Wt. Now the thing I want from here is this guy Vx also. Vx you can derive it from here, so you can just rearrange this term, you will get Ix upon NQWt. So this is your Ix and Vx which we will be using. Now what is Vh? That is important. Now how do you derive Vh? So if you see, there are two kind of forces there. One is electric force, which will develop after some time, if this will be QE, and one is this magnetic force, which will be opposite to the electric field, electric force. So in the steady state condition, there will be equilibrium and there will be no movement of charge carrier after that. So that's how you're gonna drive it, VH. So what I'm going, QEY, that is a voltage developed, from, let's say, from voltage developed, and that is electric field force, that is the magnetic field force. When suppose they are perpendicular to each other, so you can write QVB, and EY is, you can write dV by dr. So that's what my R is width of the sample, is this width of the sample, and Vy is same as Vh, and this same it is. Now if you see here, there is a Vx term here, there is a Vx term. So what you can do, you can divide by Ix, or what you do, you put the Vx value from here. As soon as you do it, you bring the Ix here, and you get Bz upon Bz. As soon as, okay, so here I have made a mistake, so this Ix is not there, so Bz by T, Bz by T over NQ. So if you can rearrange this, you can write like this. So 1 by NQ is the Hall coefficient, and this is kind of thing. So if you plot R versus B, you should get a linear curve, because this is a constant, this you're not going to change, and this is a constant. So that's so if you plot R versus B for Hall, it will go linearly. For simple resistance, it will go just straight line. Longitudinal resistance, it will just go straight line. So there is a difference between this in the Hall and the longitudinal resistance. So the idea is you divide, you have to, so in this you need to get VH through the steady state condition, and IX you can get very easily and divide both of them, you get this. So Hall resistance is Bz by T into 1 over NQ. Okay, so I'm going to talk about a special thing about Hall effect, the classical Hall effect. So the experiment here, what we are going to do here is we'll measure the longitudinal resistance in a sample, first without any disorder, and then with disorder. So the disorder means I can punch the hole through a sample. Okay, so let's measure sample without the disorder. So I mean, this is typical Hall bar geometry. You're measuring Vx through current is flowing through this direction, Vxy Hall is this direction, longitudinal. So you know Rxy is B by Ne, and Rxx is the geometry divided by Ne mu. So if you see Rxx is constant and with magnetic field, and Rxy is increasing with magnetic field. Very good. Now something interesting happens when you punch hole through this sample. So that is a kind of disorder, or you want to say punch, you say it punch. So what happens is total width, which is this, of the sample is decreased, or so the total width of the sample is decreased, which leads to the increase in the resistance, which I have shown here. This is original without disorder, and this is with disorder, that is with punches. Now if you see Rxy, there is no change in that. So in that way, Rxy is geometry independent, is a very good quantity to measure. It's not a nightmare for experimentalists. So that's what makes Rxy very special. Thank you.